we want to calculate the damping coefficient. We want to calculate our damping coefficient. We know from our measurement that K is equal to 3 kilograms. Sorry, that would not be right. M is equal to 3 kilograms, and K is equal to 43 newtons per meter. All right. Now, first, we have a number of peaks, right? We could definitely take this peak and this peak. That would be perfectly reasonable. We could take this peak and this peak. This is a pretty clean system. It doesn't actually have too much noise. But what might be the issue of taking two peaks right next to each other? Or maybe not phrase the question, but think about some of the issues of taking two peaks right next to each other, right? In an experimental system, we have a lot of variability. Might have a lot of degrees of freedom, so we'll have a lot of different frequency components. So generally, whenever we can average over more, it's better. So we probably want to take like a first peak and maybe this peak out here. That might work pretty well. Now, once we get into lower peaks, they get a bit hard to get an actual precise value for. So maybe those aren't the benefits. We could take a top peak, or we could take a bottom peak. What I would recommend you don't do is take the first peak. And that's, if this is an exam question, that'll be an issue on the exam, right? Because if you take the first peak, you might not actually have the first peak, right? If your plot starts like this, right, and you take this point, that might not be the peak. So just remember that for the exam, because that's something that will pop up if this is an exam question. So I don't want you to lose one. Just a freebie. All right. So the question actually tells us which points to take, because it's just a little bit easier. So we're going to take x1. So let's say t1 is equal to 1 second, and let's write it like this. x1 is equal to maybe negative, it's not quite 10, right? So let's say negative 9.5, and it's in millimeters, negative 9.5 millimeters. And then T2, let's go ahead and take 4. That gets me out here. That gets me a number of iterations away, so I can average. And then let's say it's not quite negative 2. It's a little bit below. So we're going to go 6 seconds. And x2 is equal to negative, just go 1.8 millimeters, right? Your results may vary. All right, so then the next question is, what is our n? So remember, before we had an n, which was the number of cycles. So if I go 1 cycle, 2 cycle, 3 cycle. So I'm going to have n equals 3. And those are the ones that I want. So I can just go ahead and put that right into my logarithmic decrement equation, and I get delta equal to 1 over 3 for 1 over n, natural log of negative 1.5, which is x1, over negative 1.8. Put that into your exam approved calculator, and you can get 0.554, probably a bit more precise than we need. But that gets you my decrement, right? So from that, I know that zeta is equal to delta over the square root of 4 pi squared plus sigma squared. So that's going to equal to about 0.554 over 4 pi squared plus 0.554 squared, which is equal to 0.0879. And so that's going to be a unitless number. But that's pretty easy now to put into C, which is equal to zeta 2 square root of km. That's 0.08, we'll just go 79 times 2 times the square root of 43 times 3, which is equal to 2.0 kilograms per second. Right, so C is equal to 2.0 kilograms per second. And when you do a test or a homework, it's always good to box your answer, right? It looks nice and clean.